Bismillahirrahmanirrahim. Hello everyone. Welcome to part 3 of our dynamic behavior video. This time we're going to focus on inverse response. So what is inverse response? Where does it occur? Well, as the name suggests, inverse response is when we expect the response to go one way, but it goes the opposite way first before it finally goes the direction that is expected. Well, it happens when there's two competing dynamics. One that is the one with more influence initially, and the other one which has a stronger influence ultimately. As explained in the previous slide, there's two competing dynamics that cause an inverse response. And you can see the two dynamics in this block diagram. There's two parallel structures that can actually compete against each other when taken as a whole to result in the final response. If we derive the transfer functions of these parallel structures, this is what we get. Can you derive this transfer function? What if we put in a step input into our parallel system? Let's say we give the gain a value of 1, tau 2 and tau 1 a value of 1 and 2 respectively. What happened? Well, depending on the value of tau 3, it affects the transient response. So tau 3 being in the numerator is the 0 in the transfer function. And whatever the value of tau 3 is, it affects the transient response before getting to the new steady state value. If tau 3 is negative, this is when we get the inverse response. If tau 3 is 0, then we actually get something like an overdamped response. This is tau 3 equals 1 and above. If after a certain value, then we have such as this, an overshoot, which will finally settle back down to the final steady state value. Now, among all these responses, which one do you think would be more difficult to control? Can you justify your answer? A very good example of a system with inverse response is a boiler. There's actually two opposing dynamics occurring in a boiler. One is from the energy balance, another one is from the mass balance. Let's say we have this cold feed water coming in, and suddenly there is a step change in this cold feed water. What do you expect to happen to the level in the boiler? The expectation is, of course, for the liquid level to increase, correct? Well, what actually happened is that the cold feed water will cause the bubbles in the boiler or the frothing to come down. So once the froth comes down, what happened is that there will be a decrease in the level in the boiler. Now, after a while, once everything is heated back up, the frothing will go back up and the level would increase again. So, as you can see from this graph, 1 is the effect of the mass balance, which is a first order system. 2 is the heat effect. And finally, once the mass balance effect, the mass effect has tapered off and gone to the final steady state value, the increase in the heat effect will take over, and this is why we have an inverse response as shown in the graph with the red colored line. Now, I want to give you an exercise and see if you can explain why there is an inverse response in the system. This is a series, reactor in series, where we have the reactant Ca coming in. This is the Ca is the concentration of reactant A, and we have a solvent. In the solvent stream, there's no A, there's no reactant. When both mixtures first go into the first tank, what happens if there is a step change in the solvent? And finally, when it goes to the second tank, what happens to the final output? As you can see here, when there is a step change in the solvent flow, you can see that initially there is an increase in the composition of A in the output, and finally there is a decrease. So what actually happened? What caused the inverse response? Try to think about it and give your explanation. That's all for now. Thank you.